Okay, back. We're going to start Chapter 2. We're not going to do Section 2.1. On the first section in each chapter, the author feels like I should have given you as homework assignment, but I don't think you're capable of doing them, so we just skip all those. So we always start the next chapters in the second section. So we are going to spend 2 days in this first section. Chapter 2 is all about the big calculus idea of limits. We ended Chapter 1 with limits, and that's where we're going to pick right back up. So I'm going to give you that definition of a limit again, but I'm going to use some symbols and shorten it up so it won't be quite as wordy. So, and we're going to talk lots about limits in this whole chapter, obviously. So definition of limit. There's a good chance you're going to have to know this definition. And the way it starts out, it says L is the limit as x approaches c of f of x if and only if there is a number delta and we're going to use the Greek letter for delta, lowercase delta. There is a number delta greater than 0 such that if x is within delta units of c, but x doesn't equal c, then f of x is within epsilon, there's the Greek letter epsilon, units of L. Okay, this next part I'm going to show you in the book what this definition actually means, and then we're going to start. So you don't have to write any of this down. I just kind of want to clear up a little bit of what's going on there. So what's happening is for this given epsilon unit, we did this before. Here's your limit of 3. They're going an epsilon unit away, above and below that limit. And then you're going to pick a delta unit close to c so that any number you pick in this window, when I pick the x value and I stick it in the function value is between these two epsilons. So think of it as windows. There's a window opening here on the y-axis, and there's a window opening here on the x-axis. So if I pick any value in here, when I go up, I want to be within this window here. So here, yes, everything fits from here to here, but if you look, there are some values outside of here that I go up and I can still be within the epsilon window. So this delta is a little bit too small because we could widen it out a little bit to include some more x's that are still within the epsilon window. Here, for this given epsilon, this delta was too big because if I pick an x value that's out close to this boundary here, take a look. When I go up, I'm below the epsilon window. So this delta is too large. They picked a delta of 1 here. So for that given epsilon of 0.8, I guess it's 0.8 here, this delta is too big because all of the values in between here are supposed to give values between here and here. And on the third one, I think you can see what's happening here. This one was too small, this one was too big, this one's just like the 3 little bears, going to be just right. So every value I find in here, when I go up to the graph, those are within the epsilon window. So our goal today is, given this epsilon window, figure out the perfect delta window. Just like we did in that last section, just that the equations are going to get a little more challenging in this chapter, or this section anyway. So we first want to start with just a real fundamental approach to it. So I want you to grab this worksheet that I gave you, this problem set 2.2. We're going to try 3 of these together. And then you'll have the rest for homework here. And then we're going to find deltas algebraically. So our whole goal here is to find I should say estimate, because we don't have any equations here, the delta for the given information. So the first thing we want to do is give the limit as x approaches 3 for this function f of x, and then find the delta. Well, all you got to do is plug 3 in. We don't have an equation to plug it in, but as I go up, the limit is 5. So my limit's 5. My epsilon is 0.5. So what we want to do, because 5 is my limit, I want to go 0.5 away. And it's just estimating halfway. So I'd be at 5.5, and then I'm going to have 0.5 below to 4.5. Now use a straight edge. Forgot to tell you need a straight edge, so if you need to hit pause, go ahead. You're going to draw the line as horizontally as you can. Once you hit the graph, you want to go vertically down and estimate that x value. So if I was estimating, I would say that x value is about 2.8. So my delta on this side, remember delta is the distance away, I'm going to say it's about 0.2 away. And because this graph kind of looks symmetrical at the 5, we'll probably get the same value over here. And we're just estimating. So we don't all have to have the exact same values here. And I see it does look symmetrical. So for this, I would estimate the delta to be about 0.2, maybe 0.3 if you estimated that. Then it all depends on how good and straight your lines are here. We're just looking for you to be in the ballpark and try to get a feel for what we're doing. So given this epsilon window, the epsilon was 0.5 away, so 0.5 above and below, estimate the delta. And I'm going to say delta is about 0.2 for this problem. Okay, I do want to try another one. Number 2. We first want to find the limit as we're approaching 6. This is where we're getting our x value. So the limit as x approaches 6 of f of x is, so if we go to 6 and we read up, 4. So 4 is the limit. I want to go 0.7 away from that. So again, just estimating. So 0.7 above, 0.7 below, making our epsilon window. Draw horizontally until you hit the graph. Then down. Okay, this one's not looking so symmetrical. Okay, on this side, I would estimate that delta to be about maybe 0.9 on this side. On this side, though, I'm going to say about maybe 0.6. So what do you do here when you've got two different deltas because the graph isn't symmetrical around this point? Remember, according to that, the pictures, whatever delta I pick, I can go on either side of my x value, and everything in there has to be within this window. Well, if I pick the 0.9 and I go way out here to the 0.9 away, and I go up, I hit the graph way before the epsilon window starts. So when this happens, you always pick the smallest delta, the smaller one. Don't pick the bigger one, because the bigger one won't work on the other side of the x value. You'll be, when you go up to hit the graph, you'll be outside of the epsilon window. So pick the smallest one. So here I'm going to estimate delta to be about 0.6. Okay, and the last one, we want the limit as x approaches 5 first, then we'll estimate delta. just getting you used to the notation here. The limit as x approaches 5 of f of x is, so if we plug 5 in, we get 2. So 2 is the limit. So we always move epsilon away from the limit. So that'll bring me up to 2.3 and 1.7. Okay, if you look here, this isn't going to help me at all. That one does nothing for me. This one hits the graph twice. So I still get 2 delta values. Five was my x value that I was approaching. Here the delta, I'm going to say about 0.7, 0.8. Here it's well over 1. It's like maybe 1.3. We don't want the bigger one. You want the smaller one. So then when I go 0.8 away on both sides, every value in there is in my epsilon window. Okay, so you'll have these 3 for homework. Now we're going to find delta values algebraically, and we did this in the last chapter. Like I said, the only thing is the equation in the middle might be a little bit more algebraically challenging. So let's try a couple. Let's see, go right here. If f of x equals 4 minus 2 times the cube root of x minus 6. We're going to let x equal 5 and epsilon equal 0.01. I want you to find the limit as we approach 5 and estimate, or not estimate, but calculate delta algebraically. So find the limit and calculate delta algebraically. Okay, a sketch might help a little bit. I'm going to take the time to graph this. 1 second while I find the calculator. Not that you have to have the graph, but it might help you in case you make a mistake. The graph might show you that you're way off. So we want 4 minus 2. The cube root is under math. Your cube root is right here, and your x root, like if we were doing a 4th root or a 5th root, we could use this. But the cube root's built in. Cube root of x minus 6. Zoom 6. And again, I am going to be finding the limit at 5. I can use the table, or I can just trace 5, enter. I'm looking right here on the graph. So and it looks like my limit is 6 based on what's showing up down here. And I could have done it here. I could have done 5 minus 6 is negative 1. Cube root of negative 1 is negative 1. Negative 2 times negative 1 is 2. 4 plus 2 gives me the 6. So I could have done that algebraically also. But anyway, so first part was find the limit as x approaches 5 of f of x. And what we're going to do is just plug 5 in there. I did the trace. We get 6. Okay, now what we're going to do is make our epsilon window. We're going to go 0.01 away from 6. So that's above and below. So what we'll do is set up our triple inequality. That's how we solve them algebraically, just like we did in chapter 1. So you take your limit and you subtract the epsilon. Put your function in the middle. And then it's the limit plus the epsilon on the outside. A lot of people, the biggest mistake they make is they grab the x value and stick it here and add and subtract the epsilon from it. That's why I think sometimes the graph might help. You'll at least look to the y-axis because you know the limit's the y value. All right, my first step then in solving for x in the middle here is going to be to subtract 4. So I'll have, that will be 5.99 minus 4 is 1.99 is less than negative 2 cube root of x minus 6. And then I'll have 2.01 here. Divide by negative 2. (1.99) divided by negative 2 is a negative 0.995. If you remember from Algebra 1 now, when you divide an inequality by a negative, remember you got to flip the sign. Okay, this will leave me with the cube root of x minus 6. Flip the sign. Here I'll get a negative 1.005. Okay, I don't like to carry the root symbols around or along. I want to rewrite this with fractional exponents. So if you remember, again, I think this is advanced algebra, the way to rewrite this would be x minus 6 to the 1/3 power. From now on, when I see a root, I will always rewrite it with a fractional exponent just because it's easier to work with algebraically later on in the problem. When it's a square root, remember a square root, we don't put the 2 there. So what this would be as a fractional exponent is to the 1/2 power. Square root's the common one, we don't put the 2 right here. Okay, so I didn't do anything except for rewrite that middle. Now what I can see easily what I need to do to get this these parentheses, this 1/3 power to go away, if you remember your exponent rules, is raise it to the reciprocal power. And the reciprocal of 1/3 is 3. So what I'm basically doing is cubing this, which means I've got to cube this and cube this. So negative 0.995 cubed, negative 0.995 cubed. Remember, if you have negative numbers raising to powers, you should put them in parentheses. And then I need negative 1.005 cubed. So I'm going to carry out about 4 decimal places. Negative 0.9851. That cancels. I get x minus 6. Negative 1.0151. Add 6 to both sides. Or to all 3 parts, I should say. Plus 6. I can get this one. This one here is 4.9849 x. Over here I will have negative 0.9851 plus 6, 5.0149. And I know I did it right because my x value that I was approaching was 5. If you go through this process correctly, your 2 values should be around the x value that you were approaching. Okay, so what I found are the points on the x-axis. 5.0149, 4.9849. Okay, this is not delta yet. Remember, delta is the distance away from 5. So I need to check both sides because this graph, just from what it looks like, does not look symmetrical. So which one's closer to 5? I'm not really sure. We'll find out here in a second. So this one, if I subtract 5, I get a delta equal to 0.0149. On this side, I've got to go 5 minus this value to get the distance as a positive value. So 5 minus 4.98490151. So the one that was smaller, remember we want the smaller one, was on the left. So there's my delta. Okay, not bad. We're also going to add something. So that's kind of what we did at the end of chapter 1. A little more challenging with the roots in here. There's an extra thing we're going to do. It's like a part B. Keep that handy. We are going to, I don't like that glare. There we go. Part B, calculate delta algebraically for any given epsilon. What that means is we're going to redo this process, but instead of putting 0.01 in, we're just going to put the variable epsilon in and carry the epsilon through. Now, we already know when we set this up that the right-hand side of this inequality gave us a bigger delta value that we didn't keep. So we don't have to set up a triple inequality for this part B business. All we need is this side here. The side where we took the limit minus the epsilon, that's the side that gave us the closer delta value. So all I'm going to do is rewrite this line, but in place of the 0.1, I'm going to put in epsilon and carry it along. So, and this is still as x approaches 5. That's why we can do it. As x approaches 5. So I'll go 6 minus the epsilon less than 4 minus 2. I'm going to rewrite that as x minus 6 to the 1/3 instead of that cube root. From now on, I will always write fractional exponents instead of the root. All right, it's the same steps we did here. The first step was to subtract 4. We're going to do that. Subtract 4. So what I can simplify, I've got 6 minus epsilon minus 4. I can combine my 6 minus 4 and have 2 minus epsilon less than negative 2 x minus 6 to the 1/3. Next step was divide by that negative 2. Okay, I have to divide. I'm going to distribute and break this apart. So 2 divided by negative 2 is a negative 1. A negative epsilon divided by a negative 2 is going to be a positive epsilon over 2. I just distributed by dividing. Flip the sign. I'm left with x minus 6 to the 1/3. Now I'm going to cube both sides. Cube. Cube. I can't do anything here. I'm just going to leave it just like it is. I don't want to cube it out and get something ugly. I'm just going to leave it like that. Those cancel. I've got x minus 6. My last step is to add 6 to this. So I've got the quantity negative 1 plus epsilon over 2 cubed plus 6 is greater than x. Now remember, I'm still at the x value. I am sitting right here. X is less than this number. Like if I was to take the 0.01 that I had in this part A and stick it in here, 0.01, this would all work out to be this 5.0149. That's where I'm at. That wasn't my delta, remember, that was my x value. So what did I do to this to get to this delta? I subtracted 5. So I'm going to do the same thing here. To get delta, I'm going to take this whole thing and subtract 5 from it. So I've got the quantity cubed plus 6 minus 5. What I can combine there is this 6 minus 5. Those combine to a plus 1. So my delta is negative 1 plus epsilon over 2 cubed plus 1. And what I can do to check my answer is put the 0.01 in there that I had in the first part, work all this out, and it should come out to the delta that I had here. And I'll take the time to show you that. Clear that. Parenthesis, -1 plus epsilon is 0.01 divided by 2, quantity cubed, plus 1. And there it is, exactly what I had before. So if I said, oh, redo this problem and put the epsilon at 0.001, well, I wouldn't have to go through all these steps anymore. I could just stick it in here and get it. So this is just kind of an exercise in algebra, and you really need good algebra skills in calculus. That's why we practice this. Let's try one more, so you know the process. Oh, no, I don't have one more. That's all I have. Oh, I only did one. So it's the same thing as we did at the end of chapter 1, except for this new part of carrying along the epsilon. So your homework is going to be to finish those 3 problems with the ruler. So finish the worksheet. Then pick up problems, what is it? I wrote it down. Problems 7, 8, and 9. Page 45, 7, 8, and 9. Oops. Okay.